We're now going to talk about analog interfaces. Analog interfaces are fundamental in embedded systems in order to interface the outside world. The physical world is indeed consisting of analog signals. Everything is continuous, both in time and in values. And in order to use the power of digital electronics, we want to be able to convert those continuous values into digital signals such that we can leverage digital signal processing. Why am I saying that we want to use the power of digital electronics? Well, it turns out that digital signal processing helps you to do very complicated digital signal processing in a simplified way. Here's a typical DSP type of flow. You will have your analog signal, time varying and continuous, going through an analog to digital converter. After being sampled and being quantized, you will receive a stream of incoming samples and you will be able to perform digital computation on that. After the digital computation is done, you will be able to reconvert back this digital information into the analog domain using a digital to analog converter. Why is this process interesting? Well, it turns out that your signal processing will be simplified quite significantly on many fronts. Here's an example. Multiplying a signal by 2 is actually multiplying the digital value by 2, which is just a single bit shift on the left. Same goes for a division by 2. An inversion will be just switching or inverting the signal. Clipping a signal will be done by an if test to clip the signal if you go above a given range. So all those operations are actually very simple to do with a simple ALU, but would require more complicated analog signals to implement that in the continuous domain. All those types of DSPs have several applications in the audio range, videos for filtering, special effects, compression, and so on and so forth, as well as data logging. This is mostly what interests us, audio and data logging in many simple embedded systems where you'll be able to get data from sensors and do some filtering, summations, average calculation, and so on and so forth before pushing this back to your actuators. Let us review a little bit of vocabulary here. ADC stands for analog to digital converter, and it is used to convert an analog signal, either in voltage or current, to a digital value. A DAC, a digital to analog converter, converts a digital value to an analog value, both in voltage or current. The sample period. When you use an ADC, the sample period is a time between each conversion, and typically samples are taken at a fixed rate. This is what you hear as, this is a 1 megasamples per second chip. Samples will be taken at 1 megahertz in that case, and that will be the sample period of your system. VREF, the reference voltage. Any analog signal you will take as an input to your system will have to be within ground and VREF, or between minus VREF and plus VREF. It needs to be in a range, in a maximum range supported by your ADC. Resolution will refer to the numbers of bits used for a conversion. For example, you'll be able to have an 8-bit or 16-bit conversion with a various level of accuracy for those different conversions. Note that the more, not always the better. That really depends on your application and on the resolution needs that you have. Would that be really interesting to just quantize noise or not? That's an open question depending on your application. Conversion time is the time it takes for a signal to be converted through the ADC. You sample your signal and you wait for the conversion time to finish before having the digital value available.